Hello, greetings, good morning, good afternoon, good evening, whatever time zone you are. Welcome to our third episode of the Bay Area Apache Spark Meetup. My name is Jules Damji, and I'm the developer advocate here with Databricks as part of the developer relations team. And joining me today is Anish, who is the staff engineer with the streaming team, and he's going to be talking mainly today. So, Anish, say hello.
Hi, folks, wherever you are.
And we also have from the streaming team, Bo and Eric, who are going to be joining us later on to answer some questions that you actually might have. They might even answer some questions while we're actually talking. But say hello to the community as well.
Hey, folks.
All right, thank you very much. And now, just to get started, logistics. We really can't hear you, but what you can do because of the nature of the live stream, just pop your questions in the chat, and we'll try to address them either live or we'll try to address them later on towards the end of the presentation. That way we keep the flow going. Also joining me is my co-host Carly, who's in the background manipulating, although we are coming live to you on YouTube as well as on LinkedIn. So keep those questions coming and we'll try to address them towards the end. Just to get the context, let's have the slides up, if you don't mind, Carly. Brilliant. Now, just to get the context, the Apache Spark streaming actually has come a long way from the early days. I had the good fortune to be part of the community from very early days. Back in Spark 1.0, we actually had D streams, which was an abstraction on top of the RDDs. And it was a bit brittle. It was a kind of not very fault tolerant. But as time went by with 2.x and with 3.x, we actually included a lot of enhancements, such as exactly once semantics, window aggregation, triggers, window aggregation, and all that, which included fault tolerance. And then 3.x and 4.0 has had some significant increments. And then in 4.0, we actually have more improvements that allow you to write, more use cases of structured streaming. And so Anish is going to be sort of walking us through what this thing is all about. And just before I hand it over to Anish, I just had one more announcement to actually make about, next slide, please. I just had one more announcement to make about the Data Plus AI Summit, which is coming up in about a month. Those of you who have attended it, please would like to see you again. It's on June 9th to the 12th. There's a link over here. Please feel free to click on it. And we're going to be having lots of movers and tech leaders and shakers. So be part of the conversation. You probably won't miss it. If you're joining us from around the world, please say hello on the chat. We want to see where you are coming from. And having said that, I'm going to not waste more time and hand it over to Anish to get us started about, what's all TransformWithState is all about in Apache Spark 4.0. Anish, take it away.
Yeah, cool. Thanks, Jules. Thanks for the introduction. Hey, folks. My name is Anish. I'm a software engineer on the streaming team at Databricks. Bo and Eric also work on the same team along with me. And today, for our agenda, we're going to talk about a bunch of streaming, sort of a high-level overview, then dive into stateful streaming in Spark, and then talk a little bit about what's coming in the upcoming 4.0 release, primarily around TransformWithState. We'll talk about what all functionality has been added, what all you can do with this brand new operator, and then some stuff around usability, right? Essentially all the native integrations that we support, all the new sort of enhancements, features that we have added. So all those things we will cover through the next hour or so. We'll try to keep some time towards the end for questions. So, if you folks have questions along the way, feel free to bring them up, and then we'll try to get to them towards the end. All right, so let's begin with a streaming overview. As many of you know, real-time data is creating a lot of opportunities. All of your organizations, are generating a lot of data from various data points. You have point-of-sale machines, banking transactions, news feeds on the social media side, weather data, environmental data, sensors in a ton of places. For ads, you have like click data, ad streams, and so on and so forth. So a bunch of new data streams are changing the way we think about data, and it's also creating a lot of new opportunities for us to interact and enhance what we can do with this data and turn it into information. Across the board, in various verticals, various sectors, you see a bunch of use cases on the streaming side, all the way from fraud detection to content recommendations to in-game analytics, vaccine distribution, so on and so forth. So pretty much every sector has use cases that could benefit from streaming real-time data. Now, why do we talk about streaming with Apache Spark? Apache Spark, as you all know, is a very popular query processing engine. The unique advantage that Spark brings is that it is a unified engine for batch and stream processing. So you can write, as many of you might be aware, you can just do like a spark.read versus a spark.read stream, and effectively we'll convert sort of the batch query into a streaming query. You can just need to provide the checkpoint, and we'll keep track of how far your query has progressed, help you to perform incremental processing, incremental compute, so on and so forth. So effectively, it's a very powerful semantic for someone who is already accustomed to the batch side in Apache Spark, and they can just tweak it very easily and start streaming with the data sources that they have. As I mentioned, it is fault tolerant. One of the cool advantages that streaming queries have is that all the state is checkpointed in terms of the offsets, the commit logs, the actual state belonging to the state stores. All of this is kind of written to some sort of an object storage, and we will ensure that if the queries fail or if your nodes crash, we can recover from a safe state and continue processing without needing to reprocess the entire data. Spark, as many of you might know, works with the notion of a microbatch sort of a concept. It is more throughput oriented, but you can also tune it according to your latency and throughput needs, and it can be super cost effective, even for cases where you might want to do available now triggers, or where you're processing data in sparse intervals or with a higher throughput. All of these use cases tend to work well with Spark structured streaming. It has a bunch of easy to use and powerful operators, from stateless operators to stateful operators, primarily the power of the data frame API that helps you to sort of read data, ingest data, transform data, and then potentially write it to multiple sinks as needed. Advanced stateful processing is another big area. We'll cover more about this through the presentation today, but this is getting more and more powerful as new use cases are built on top of structured streaming. All right, and it's not just, many of you folks might know that streaming is becoming more and more popular within the Spark landscape. It is something that we also see on the adoption side within Databricks. Now we have close to like about 28, 29 million weekly jobs that are streaming, that are running on top of the DB platform. This is a significant increase that we have seen. Like last year around the same time, we were maybe around 18 million. A ton of use cases, a ton of significant amount of revenue also being driven through streaming, as you can see in the graph here. So we continue to see strong adoption for streaming on top of DB and on basically using structured streaming in Apache Spark. All right, so since we want to make sure that we have a lot of time for diving into the technical details for the features that we're introducing, let's jump to stateful stream processing. I kind of am assuming that most of you might have a high-level overview of what structured streaming does. But for those of you who might not, essentially, you can think of streaming as sort of reading from a bunch of sources, and most of them likely, they might be idempotent sources, replayable sources or non-replayable sources, and we read from them and we keep track of the offsets. And then effectively we would write, you could perform any transformations, and then you would write to the sink. And so there are, at a high level, two classes of queries, right? Like one is a stateless query and one is a stateful query. As you can imagine, stateless queries are essentially, primarily reading from a source, performing some stateless transformations like filter, project, whatnot, and writing to some sink. Whereas stateful queries need to look back and keep track of what happened in the past, right? And the way we allow that is effectively through something called as a state store. And that essentially allows us to record information as it has happened with the real-time events, and then decide what to emit, when to emit, and so on. As many of you might be aware, today structured streaming largely powers, more throughput-oriented ingestion, ETL, like sort of analytical workloads. Even if they are stateful, typically what we have seen users do is that they might perform some aggregations, or they might perform some sort of state machine logic, and then write to some sort of a storage layer such as Delta, and then have the analysts, the business analysts, or other personas effectively read that or query that data from the SQL warehouse, and then use it for some dashboarding or some after the fact analysis, right? However, in the future, we want to make sure that structured streaming is also catered to power to the more mission critical operational type of workloads, right? So, think fraud detection, predictive maintenance, health monitoring, all of these, cases where you might need like low latency real-time alerting. These use cases are something that we want to ensure that Spark also, can power in the future. Most of these use cases, from what we have seen, effectively have a combination of reliance on like state management, on some sort of like OLTP sinks, or like you have your custom sinks within like for each or for each batch. And then of course we want to ensure that there is like consistent performance in terms of throughput, latency, and whatnot. So we want to effectively cater to these use cases. These use cases also have another property is in that they kind of always tend to read and write from message buses. So think like having sort of a operational stream, reading from Kafka, doing stateful transformations like some operational logic, and then again writing to Kafka, and then you can have subscribers that potentially might pull from Kafka, and then alert downstream services or downstream consumers for for whatever actions have been taken. All right. So at a high level, right, like when we think about a stateful streaming query, we have a few different components. So we have the input, we have the output, we have the local state, and then we have the remote state, and then we have the application logic, right? So effectively think of data that is coming in to your pipeline. You want to read that data, you might want to perform some business logic, some transformations. You might also want to store some information into a local state store, and you want to ensure that there is fault tolerance, right? Like if the query were to crash, if you were to lose some nodes, or so on and so forth, you want to ensure that you don't need to reprocess the entire data from the source. So there are two reasons why we want to avoid reprocessing. Of course, one is that on the source side, your retention might be lower. The query might have made progress beyond that time interval. So if we want to go and replay, you might not have the data in the source. So you might not be able to reprocess and sort of generate outcomes on that data. And the second thing, of course, is in terms of cost, right? Like we want to be cognizant about like compute cost, storage cost, and whatnot. And we don't want to incur unnecessary penalties in terms of cost for reprocessing these queries. So the way we avoid that is effectively we keep track of the state for you. So in terms of, like we keep track of the offset logs or the source metadata or the commits, we also keep track of the state. And there are multiple modes that we use to keep track of this. You can have like full snapshots, you can have deltas, depending on the store provider. You might have different configs that you can use. So we have a few checkpointing sort of techniques that users can enable, and they can sort of change the way the shape or performance of their queries looks like. All right. Now, when it comes to user-facing APIs, right? Like if you're a user for Spark structured streaming and you want to do some stateful stream processing, what are the options that you have today, right? Like before the release of the upcoming Spark 4.0, today you effectively have some built-in operators and you have arbitrary stateful operators. Built-in operators are essentially operators that allow you to just specify the operator name within the data frame operation, and you just provide a couple of arguments. They're more user friendly. They effectively do only one single thing. Like for example, you have dedupe, you have aggregation. You can think of like group by count, get the max, min, apply some aggregation function, or like drop duplicates, like effectively just to do dedupe on the set of incoming events on the stream. If you want to do stream joins, like time interval joins or session windows, these are kind of like very clear cut, well defined built-in operators that do that exact specific thing. And then you have the arbitrary stateful operators today, which are like map groups with state and flat map group with state, right? The only sort of main difference is whether your use case can be satisfied with the built-in operators. If you're doing some simple transformations or simple aggregations, likely it's possible that you can get away with just using the built-in operators. But from what we have seen is that customer use cases are much more complex than that. They want to do some custom processing. They want the flexibility to manage the state, to evict the state, and so on. And so they do tend to prefer some of the arbitrary stateful operations as well. Now, having said that, of course, the built-in operators are optimized, kind of to perform only exact that specific operation. So if you end up finding that your use case is well served or better served using the built-in operators, we definitely encourage users to use that model. All right. Now, when we talk about arbitrary stateful operators, today the only option that is available in Apache Spark is this operator called as flat map group with state, right? Now, this, as some of you might know, is kind of an evolution of the existing like map group or flat map group operator within the batch side of Spark. And then this evolved to effectively add the with state component, essentially, because along with doing the UDF kind of processing, we also allow users to interact with the state. Now, this essentially just supports like a single user-defined state object per grouping key. As you can see within the example here, we pass this group state object as something that the users can interact with, and they can update it, essentially while evaluating the current set of values that are passed to the operator. And then they can change the state, they can retrieve the state, and then effectively write it out, and the new update will be available in the next batch. Now, this is kind of a simplistic API that Spark used to, had provided till 3.5. However, we heard from a lot of users in the open source community, a lot of like customers as well, where they were complaining that some of these operations or some of the functionality or features provided by this API are not sufficient or not powerful enough to solve for the use cases that they had, right? One major complaint was that users do not have the flexibility to model their data in terms of the state data. we only pass a single object. They cannot split it. They cannot define like different types. They cannot conditionally update some of those instances on a per event basis. The second aspect was a lack of composite types. Flatpak group with state effectively just allowed you to deal with a single group state object. It had no notion of sort of language level primitives, or like as different languages have sort of collections such as list, array, map, priority queue, and so on and so forth that might be optimized for the underlying storage. Flatpak group with state does not provide any of that. So you're forced to, for any update that you have to make, and let's say it's a list type and you just want to do an append, you're forced to actually read the entire data, deserialize it, add the changes, serialize it back again, and then write it out, which is much more expensive than most people would want. There is also no automatic support for state eviction. There is no support for state schema evolution. So not very flexible, sort of powerful from a performance, usability, flexibility standpoint. All right. So given that we had seen all of these issues, and clearly we wanted to address some of these challenges for the open source community to make Spark even more powerful than what it is today. With the upcoming 4.0 Spark release, we are excited to announce TransformWithState as another very powerful operator in the bucket of tools that you folks will have in the future. All right, so what is TransformWithState, right? So TransformWithState, you can think of it as the next generation, or even effectively as a replacement for the Flatpak group with state operator. Anything you can do within the Flatpak group with state operator, you can do within TransformWithState, and you can do significantly much more than that, given all the functionalities that TransformWithState offers. It is supported in both batch and streaming modes. This is in line with the Spark philosophy that we want a unified API. We want users to, if they just want to get used to how the shape of the API looks like, they can try it out in the batch context first, maybe run some unit tests. And once they're comfortable, then they can move on to running their streaming pipelines. Of course, for some of these stateful pipelines, the state essentially, is not super relevant for the batch sake, but it'll just give you a sense for how to use the API, what are the different components, how they interact with each other, so on and so forth. Now, the cool thing about TransformWithState is that it allows users to now specify their business logic in an object-oriented manner. We had this sort of single function Lambda style of approach within Flatpak group with state, which was potentially not potentially not sufficient for many of the use cases that we saw. So we allow users now to model their use cases in an object-oriented manner. They can define the stateful processors, they can define the inputs, they can define the data types, the data members. They can define the encapsulation, inheritance, all the nice properties that come with the object-oriented programming. As with some of the elements that we have retained, we now give you even more fine-grained access to the input events, to the state, to the output events. You can decide how you want to process, how you want to store, how you want to emit, and also in terms of timers and callbacks for performing event-driven processing. Now, how do you actually define a stateful processor, right? Some of the syntax is slightly different between Scala and Python, but you have an example here on the Scala side where I have defined a case class for some transaction info, which I can use to essentially map the state. I have this sample sort of fraud detection processor. I'm defining the state variables or the class private members. And then I have this init method where I'm going to initialize them, provide a name, provide the encoder, provide whether they need TTL enabled or not. And then I can sort of handle the input rows as they come. So you can see like if we passed a single key, like the grouping key, and a set of values corresponding to that grouping key, and also timer values that we'll talk about in the next few slides. Now, one thing that you can note here is that all the stateful processing that Spark does is effectively sort of based on the split for a grouping key, right? Like, so for a stateful query, there is a notion of shuffle partitions. So as many of you might know, the default shuffle partitions in Spark are 200. You can change them as you need, depending on the load volume of your specific query. For all the data that is flowing through your pipeline, you effectively would group by a specific grouping key. And for that grouping key, a certain set of keys will land on each partition. And for those keys belonging to one partition, you can assume that this function for handle input rows will be called once for each unique key that is belonging to that partition. Note that this stateful processor that is invoked, like a large chunk of it, like, in terms of the initial state or the input rows or the timers, is invoked on the executors as part of the task execution, so that we can kind of, shard the keys across, multiple partitions, and you can effectively process all of them in parallel. The same key, of course, lands always on one and only one unique partition. So as even if new events appear for the same key, we know that they will always land on the same partition for that specific key. Now, just in terms of the high level structure, we have like 3 or 4 steps. You define the input schemas, the output schemas, the state schemas. You initialize the state variables. If you have initial state, you will also initialize the query with that initial state. And then you would handle the input rows. You would also handle expired timers if you have any. And then, you produce any output rows as needed. And you can also, register, list, delete timers as well. The intent of this stateful processor, or the intent of how we want to perform this stateful processing, is mainly to give control to the users, right? So users are defining how they want to specify the input schemas, the output schemas, the state schemas, define the watermark, define how to do eviction. For the large part, it's primarily in the hands of giving users the flexibility they want in terms of handling these scenarios. All right. Now, the next thing, so let's say you have this operator that you want to use within a streaming query. You need to define a stateful processor. Within that, you have these methods. For the state variables themselves, we now allow users to decide which data structure, or which composite type they want to use, right? In the past, we've had this problem where each operation or each update had to have like a read, modify, write kind of a situation, which was very inefficient for certain types of operations. You can imagine if you want to do appends to a list, or you want to do point lookups on a specific key within a map type, we only need to read or store that particular row within the state store. So we don't need to read the entire data associated with that particular structure, and try to deserialize it and perform some of these expensive operations. So currently with the 4.0 release, we are supporting value state for sort of a single primitive type of state object, list state, as you can imagine, more like sort of a linked list, and then a map state, more like a hash map, which effectively will allow you to do point lookups effectively. Of course, you can also split your processing logic, operational logic, across multiple different state variables. You can decide how they need to be updated. You don't need to update all of them for every single operation, every single function invocation. So all, as I mentioned, some of the operations are also optimized, and we also allow you to add and remove state variables within the same checkpoint location without actually throwing away the query at all. One of the aims or one of the goals that we are trying to move towards is because many of these pipelines are now becoming more and more mission critical to users. They don't want to start with a new checkpoint every single time. They want to retain as much as possible and continue from there. So all of these flexibility, enhanced usability operations is something that we are looking to support with open source Spark as well. So, all right, so one new addition with the TransformWithState operator is this notion of timers. Some of you might know that we had this notion of like a fuzzy notion of timeouts within platform group with state, where you had to kind of set it on each row, and then it had to be cleared, and then it updated, and so on. And it was not really like a true notion of timers in the real sense of how event-driven applications would work. So we've now added support for first-class timers so that you can now write your event-driven programs. We support both time modes for processing time as well as event time. Processing time is essentially just based on the wall clock time. Event time is effectively based on any timestamp column that you have within your data itself. Processing time, kind of keeps going, like as the wall clock changes. The event time changes are more tied to the data that you have. Know that there is no way to effectively advance the watermark artificially today in Spark. So it is tied to kind of how the events actually can make progress. And then you can list timers, you can register timers. They will be checkpointed. The state will be kept within the checkpoint directory. You can register multiple timers per grouping key because we want to allow you to do different types of windows. Let's say you want to do sliding windows, tumbling windows, different types of session windows. All of these are now possible, and you can decide how you want to sort of encode them for your specific use case. And another thing is that as soon as the timers effectively expire, like within the microbatch mode, they will be fired in the earliest available microbatch after the expiry. Okay, another new use case or another new feature that we support is something called chaining of stateful operators. We had added support for some of these operators in the past. Platform Group with State used to support this for processing time, but we kind of never had support for event time. And this was sort of a recurring theme. Many users complaining about this because effectively, if we don't support chaining within the same pipeline, they were forced to write the output of the first operator into something like Kafka or Delta, and then again read from there, and then perform additional transformations, and then write it out, which means now you have 2 checkpoints, additional storage, additional latency that comes with the intermediate tier. So now we allow you to actually run even multiple stateful operators, like multiple TransformWithState operators within the same query. You can also specify which event time column you want us to use from the output for the first operator, and then we will use that to perform like late record filtering, also generate the watermark values for the next operator that you can use, and perform any sort of logical processing that you need to. So this allows you to not have to write to another external storage medium, and it can help greatly with cost and performance. All right, another use case that kind of comes often was like, with Platform Group with State, we always had this notion where you had to explicitly clear the state. If you kind of forgot, you could not, keep track of it. You had to rely on getting some of the metrics in terms of the state size or the number of keys or the memory usage from the progress metrics that the query emits. But some use cases, like, let's say you're just keeping track of some transaction IDs, you just want to keep them for a specific window. You don't kind of care about them after some time interval. And then many government regulations might require you to actually not, ensure that the data is erased. So in order to support some of these compliance GDPR related use cases, we also support automatic cleanup for particular variables. Users can define them on any state variable. You can define like a TTL config with a timeout duration. And once, like if that particular sort of state has not been updated till that time, we will consider it for eviction automatically, and the users don't need to do anything additionally apart from that. All the composite types in terms of like value state, list state, map state are supported. For list state and map state, the TTL expiry is on a per event basis, like a per entry basis. So we will only clear entries that, within a list or within a map for the map key that have actually expired, and not actually, remove everything within that particular structure. So this is, this should be incredibly useful for people who kind of, were trying to deal with when to clear the state, what will be, how much storage it will occupy, when it will be removed, and so on. So it takes that complexity away from the users. Another cool aspect is around state initialization. We kind of had, like, again, fuzzy support for this in the existing operator. Upland Pandas with state did not support this at all. With TransformWithState, you can now effectively initialize any sort of query with any data set that is coming from Spark. It can be like, let's say, a data frame that is reading from Delta. It can be a data frame that is reading from an existing state checkpoint. You can parse any sort of schema. And as long as you can align it with the grouping key that you use for the stateful streaming query, you can use the same model to initialize the state from any existing persistent stored location. And then this can be used for, cloning the streaming queries. They can, you can do sort of like A/B testing if you want. So all of these things are possible with the new approach. All right. So shifting gears a little bit, some other features that we added are more, aligned with the state schema evolution. As you know, there are like two parts of state schema evolution. One is the key side schema evolution, and the second is the value side schema evolution. Originally, Spark did not support any of these, right? Like effectively, most of the key schema and value schema was kind of fixed within the state schema and the operator metadata that we used to store within the checkpoint directory. And we essentially only supported one encoding format in terms of, how the state could be encoded within the state store and also written persistently to storage, right? One option, the only option that we had till 3.5 was serializing unsafe row. Unsafe row is Spark's in-memory format, like, sort of unsafe row internal row, like the in-memory binary format that we use for storing the actual row data. And as far as the state of the structured streaming engine was concerned, what we used to do is we used to serialize this data and write it out to the storage layer, and then effectively also to the checkpoint directory. But this format itself, does not have any support for schema evolution, and it's also not a stable persistent storage format as such. So it was meant to always be an in-memory format, which could potentially evolve across Spark versions. But because kind of streaming uses it, we have to we ensure that there's always backward compatibility that is maintained. But on its own, it's sort of a binary sort of packing format, which doesn't naturally allow for schema evolution. So with the 4.0 release, we are also adding an option for users to use Avro as an encoding format for their stateful streaming queries, which will give us more advantages. One primary advantage that we would get with Avro is that Avro has a lot of inbuilt support for schema evolution. It can help us do validation against schema changes in different sort of models, like backward transitive. There are a bunch of models that Avro allows for, and across a bunch of changes without doing any full rewrites on the state store. We now allow for stateful schema evolution on the value side. On the what I mean on the value side is basically for any state that is defined by the user in terms of the state variables, that is effectively on the value portion. And in this case, we support like a bunch of evolution operations. One is type widening. Let's say you started with int, you realize that it's no longer sufficient, you want to move to long, that will be supported. Let's say you have a case class, you want to add a new field, we can support that. If you want to remove a field, we can support that. If you want to reorder the columns, that will be supported as well. Renaming and type narrowing, of course, we can't lose precision or we would effectively lose data. So those are some of the operations that are not supported. So it's more or less in line, with what Avro effectively supports. But this again is a big addition for users who have, some updates or changes to their sort of incoming schema on the source side, and where it might translate to requiring changes on the schema for the state side as well. Let's say you have like a new group ID column that is added on the source schema, and you want to incorporate it within the state because you also might need to do some aggregation, or you might need to emit it in the output as well. Earlier, there was no way for us to allow that. You had to sort of, redefine your schema, throw away the checkpoint, and start again from the beginning, reprocess the entire data. Also, all of that is now possible with schema evolution when you set the encoding format as Avro. All right. So in terms of language support, from the get-go, earlier, for Fragment Group with State versus Applying Pandas with State. Just for folks who are not aware, Applying Pandas with State is the same as Fragment Group with State. It's just the Python name for the same API. We kind of did not have language parity support. Like even now, like Applying Pandas with State does not have support for some features that the Scala version has. But Transform with State has full support for Scala, Java, Python from the get-go. Panda support is already available in 4.0 or will be available in the upcoming 4.0 release. For users who are more conscious about latency implications, who don't want to pay the overhead of Pandas conversion from the Arrow data frame, for those users, we are also adding a new native Python row interface. However, this will not be available with the 4.0 version, but it should be available with the Spark 4.1 release as well. So you can choose, if you're more comfortable with Pandas, if you don't have like stricter requirements in terms of latency, if you want to make use of some of the strong collections that are available, libraries that are available on Pandas, feel free to use that. If you're more conscious from a performance standpoint, feel free to use the Arrow API within PySpark. All right, so I spoke briefly about some of the user-facing APIs that are effectively available, but internally, to make all of this work, we had to add a bunch of new things within the Spark code base. One is around how to deal with multiple state variables. For that, we added this notion of virtual column families. We keep track of how the VCF, like the column family IDs, are assigned, how that encoding happens, how we can make it efficient, how we can scale, as these number of virtual column families are added or removed, how we can support list type, like sort of append operations cheaply with the merge operator within RocksDB, allowing for secondary indexes for timers, TTL, so that we never perform any full scans for any of the functionality that we support. We have native encoder types for like doing efficient prefix scan, for doing sort-oriented range scan. We support all different types, to implement like a bunch of IEEE protocol, like RFCs and other changes to ensure that all of these data types on the struct type are supported efficiently. We have to make a bunch of operator metadata changes in order to support keeping track of the multiple column families in order to keep track of the state schema files belonging to those specific column families, how we deal with schema evolution, the interfaces in terms of how layering could be implemented so that potentially we can add other types in the future as well. So a lot of work kind of went on behind the scenes in order to bring all of these improvements to the Spark community. So we had like more than 100 plus PRs that were merged in OSS in the last about year or so. If you folks are interested in looking at any of the internals, it's all available in open source. You can check out the GitHub. And you'll find all the details for all of these PRs. If you have questions on those PRs, feel free to post on the discussion threads on other mediums, and we will answer your questions. All right. Then coming to the usability section, we cannot adding the APIs. Optimizing for performance, scalability, ensuring that things work efficiently is one part of our goal. But the second part is also to ensure that we have native integrations with other features within the Spark ecosystem as well. One recent addition that we added with 4.0 is the Spark data source, state data source reader. Earlier, we did not have any support for actually reading the state from a checkpoint location. So users were, primarily flying blind. They had no clue of, whether what is being updated is correct or not, whether there are sort of any corruptions, any sort of mischanges, anything like that was not easily visible. So we added the data source reader with 4.0, which allows users to read the state for built-in operators, for joins, for platform group with state as well. So we wanted to ensure that the same native support is available from the get-go for TransformWithState. Now, of course, this is much more complicated for TransformWithState because you can now have multiple state variables. You can have different composite types. For like list and map, you might not have enough memory, to serialize or materialize them in a single. Like if you read them together. So we add support all of these so that you can read the change feed, you can read the list and map as like either array type or map type. You can also sort of flatten them and read them as an iterator or a single row. So all of these options are available for users to use within 4.0. And we have kind of ensured that all the schema versions and all the ways you can read the data can also be integrated with the way you can provide the data frame to your initial state as well. So if you have a query that is written using TransformWithState and you want to populate let's say some variables from that and use that for a second query, that is also possible with the new API. We integrate also with Spark Connect. Spark Connect, we kind of don't have that support in 4.0. So you'll have to still rely on classic Spark SQL for now. But with 4.1, if you want to develop with local IDE, you want to use Spark Connect, that support is also in place. And as I mentioned, we also have the PySpark row-based interface. So we also did a bunch of experiments also with the open source model of Spark. Here we had like a Kafka to Kafka pipeline with a stateful processor that was doing some custom aggregation windows. And as you can see, like the P95, P99 for like 100K is about like a second or so, sometimes less than a second, depending on the use cases that you have. And even for like 1 million rows per second, still less than like one, or maybe slightly over like 1.5 seconds. So really low latency. Of course, you can optimize this further depending on how you have designed your use cases, what the stateful processing logic looks like, and also make use of the different primitives that we offer in terms of the composite types as well as other efficiency primitives. All right. Now, in terms of best practices, the same concerns that you have for streaming pipelines today running Spark structured streaming pretty much also apply to TransformWithState. One of the main things that we ask users to be careful about is configuring the shuffle partitions as needed. If you have too many, we have to run tasks for those many number of partitions. You might not have data that is spread across those many number of partitions. So effectively, it's sort of wasted processing. So we don't want to sort of allow for that. We don't want to encourage that. The second is, of course, if you have too few and the volume of your input size grows and your state size grows, you might be in a position where, effectively it's not efficient or performant for the size or scale of instances that you might have. So currently, sort of be a little bit conservative in terms of configuring the number of shuffle partitions that you allow for future growth. We don't support repartitioning yet, but that is also something that is on the roadmap and the radar for structured streaming. And also sizing the cluster appropriately, right? Like if you're running mission critical workloads, we strongly recommend avoiding spot instances. If you lose executors, we have to reload the state from the cloud, which is an expensive operation. So as much as possible, if we can maintain spatial locality, if you can sort of ensure that the task durations are within the range of the standard deviation, you will continue to get consistent performance from your streaming pipelines. Internally, in terms of feedback and adoption, we've seen like very positive feedback overall from DB customers. We have like more than 15 customers running like 4,000 plus queries just in the last quarter, like just in the last 3 months. We've only been in public preview for like, on the DB side for the last 2 or 3 months and seen like significant adoption across both Scala and Python. Python, currently, of course, being more widely used so far, but we're also seeing an uptick in the Scala adoption as well. Just in terms of the limitations, just something to note is that this operator is currently only supported with the RocksDB state store provider. Some of the optimizations, it is easier for us to just implement them with RocksDB. We do want users to encourage using RocksDB more and more with the in-memory HDFS-based state store provider. Potentially you have two issues. One is that you might run into out-of-memory issues. And the second is that you might run into these long GC pauses. So it becomes hard for us to ensure that you have consistent performance. Also, we could land in these out-of-memory issues as well. And then state TTL is also supported only in processing time. Initially, we did not find a strong requirement to support this in event time. Also, the semantics could be interpreted in multiple ways. But if you folks want to see this feature, feel free to let us know. If you want to contribute, you're more than welcome, and we can help review those changes. In terms of availability, as I mentioned, all of the features will be available in the upcoming 4.0 release. For Classic Spark, for Spark Connect, it will be in 4.1. If you are a Databricks customer, all of these features are already available for assigned clusters, and in 16.2, in shared clusters, it's available in Python. And then for Scala, they will be, we are working to add this support pretty soon. Just some resources that folks can refer to. We have a bunch of docs. We have a bunch of examples. There are like internal, external blogs that are available. People have written their own examples. So feel free to check them out. Feel free to experiment with it, try it your own examples, and let us know, how you think about the usability gains. In terms of future work, we want to continue adding, like, WithState can, as I mentioned, we don't have an efficient way to retrieve at a given index, like similar to an array. So you might want to support like array state. We've also had some asks where people want some sort of a sorted structure, like a min heap or a max heap. So that is something on our radar as well. And also look to add like additional windowing capabilities, new operators, new functionality support like CEP. So keep a watch on all of the new and upcoming changes within structured streaming over the next many years. In terms of other features, so TransformWithState is one big change that we have done. Along with that, we have a bunch of other features and enhancements coming across like different releases. You'll find like checkpoint integrity verification, like snapshot lag detection, some revamped locking changes, join using virtual column families, a new street checkpointing format, a bunch of features, a bunch of active development happening. So feel free to check them out, use them as needed in your pipelines. And of course, we welcome any feedback. Just want to note, although I'm giving the talk on behalf of our team, this is a team-wide effort. A lot of hard work gone in from the Databricks query engine team, like the streaming query engine team. So Jing, Eric, Bo, Bhuvan, thanks a lot for all of their contributions. Also, so as some of you might already be familiar with some of these names, like Juntaek Lim and Hyukjin Kwon, has helped us significantly, getting through all the reviews, commits, PRs in open source Spark, and the remaining team at Databricks as well as the broader Spark community, without which all of these things would not have been possible. We welcome you to join the community. We welcome you to contribute to some of these features that we have on our roadmap. If you want to start out by taking small tasks, adding documentation, that is also more than welcome. So we look forward to seeing more and more of you in the Spark community. And just one last note that I will end on. I will also be talking at the Data AI Summit that Jules mentioned. In this talk, we will go even more deeper for a specific use case. So you'll get like even more hands-on sort of experience with all the code, how to build the pipelines, things that you might want to be cautious about. And if you have any questions, if you want to chat with us about your use cases, meet with me and my team, we are welcome to do so, and we look forward to meeting you at DIS 2025. And that's it. And we can now open it up for questions. Jules, I think you're muted.
I think the host unmuted my mic. Carly, can you unmute me?
Yeah, I can hear you now.
Okay, brilliant. Yeah, thanks a lot, Anish. This was actually a very expansive explanation of all the good features which the community and you and the team has actually packed into 4.0. We had, fortunately, a lot of questions were already answered live by Bo and Eric, but a couple of things that I thought would be good for us to sort of address for another 5 minutes. We can stay over time. Can you give an example of a use case where TransformWithState would significantly improve streaming logic in a Python-based pipeline?
Yeah, sure. So as I mentioned, for Python, we have support for pandas as well as the row-based interface now. For pandas, effectively, this ability for you to initialize state, to define logic across multiple state variables, define the schema as either like string or DDL type, um, perform event-driven processing using timers and callbacks, conditionally update some of these state variables. So none of these, features or functionality, as well as schema evolution, right? Like, so none of this functionality was even available within the Apply and Pandas with State offering. So you can significantly revamp, your logic to make it much more simpler, much more object-oriented. Take advantage of all of these new features, take advantage of the efficiency gains from the composite types. So it should help you greatly with usability and performance.
Brilliant. And that speaks to, a couple of questions that actually came up. How is it different from pandas with apply state, which both you and also the team answered the question that it's more extensive because it provides you all these additional features you can actually do. Another question that comes from Dylan, I think he's sort of more interested in, does the state initialization feature depends on the connector? I'm not sure what connector is referring to, but he's given an example. For example, can you getting the data from, say, Kinesis, I believe he's talking about the Kinesis connector with Spark, using the AWS Lab connector. Okay.
Yeah, so as long as you are able to read the state that is written from that specific connector, that is possible. Now, of course, like, as far as the checkpoint is concerned, even the connector is only storing state about the offsets and the commit logs and so on and so forth, right? Like, we are not actually storing the data that is flowing through your pipeline. So if you are storing the data in some location, let's say you're storing it in Delta or in some other form, or let's say it's in Kinesis and you want to read it as a data frame, as long as you can read it as a batch data frame and it has the same grouping key that is associated with your streaming pipeline that is doing transform with state, that is allowed. We will be able to support that.
Another question that would it actually make, this is from Tujek, I hope I'm pronouncing the name right, on YouTube. Would it make sense, and is it possible to run multiple transformation with state operations in parallel, like running different logics that are independent from each other or on the same streaming data source? That's an interesting question.
Yeah. So you can run multiple stateful, transform with state operations in parallel. Effectively, that is like running multiple streaming queries. One thing I wanted to clarify is that the operators that you use in one streaming query do not interfere with operators in another streaming query. So the state and all the checkpoint information is local and specific to a streaming query. So even if you have multiple queries, or like, you want to run multiple operations reading from the same source, they will be checkpointed independently. So they can make progress on their own. You can write your transformation logic on each of the pipelines, and you can run both of them in parallel. No issues with that.
So in 3.0, I mean, I remember in 3.0, we actually introduced, it was 2.x or 3.0, where we introduced support for local state for using RockDB for maintaining the state. Do we still continue supporting RockDB, or actually I can have other internal high performance key value store?
So currently we support RocksDB and like sort of this in-memory HDFS based provider. We recommend users to use RocksDB as the go-to sort of state store provider. Effectively, because we can optimize it more for how we can interact with the mem tables, the SSD files. We don't use write batch anymore. We've disabled the wall. So a bunch of optimizations on the RocksDB side as well.
And in one of the diagrams, you actually had a diagram that actually showed that you actually writing stream to RockDB and then checkpointing to the permanent storage. How configurable that is? How often do you actually can do checkpointing?
Yeah, so all of that is configurable. So we try to not perform any expensive operations in the hot path. So effectively, any changes, updates, like if you have enabled changelog checkpointing, will ensure that they're only written to these changelog or delta files. We also don't perform like flush operations, every single batch. So we would only perform them periodically. The second aspect is that we don't do any uploads also in the hot path as much as possible. So some of this is also taken care of in the background thread as part of the maintenance task and as the maintenance pool. You can configure how often you want to do this, often you want to run maintenance, what thresholds you want to use. So all of this is configurable depending on the specific requirements for your pipeline and your use case.
And the permanent storage, that by default, you mentioned about Delta. So we actually storing in Delta tables, or is that?
No. So
okay.
Yeah, so the permanent storage is
the Delta files is just incremental Delta.
Right.
Okay. I just want to make sure people don't get confused. Go ahead.
Yeah, so persistent storage, essentially what I refer to is something like an object storage path. It can be S3, it can be GCS, it can be Azure, or any sort of persistent storage path that is reliably available so that we can perform fault tolerance and checkpointing. Delta tables themselves also, underlying are backed by Parquet files on S3, but Delta is a separate storage protocol and a different format than the checkpointing format that structured streaming uses.
And the checkpointing format both on local state and persistent state is the same, right? You're just doing a write of that particular.
Yeah, so I mean, there are some some optimizations that we do, so it's not exactly the same. Like we try to do SSD file reuse, so we don't have to upload the same files each time. So there are some changes around what the metadata looks like, how we can pack and compress some of that on the object store. So there are some optimizations, but we can translate between what needs to be written to local versus remote, as and when those changes are needed.
Okay, we'll take two more questions. I think this is something that I was thinking about. One question is from Deborah on LinkedIn. He said, are there any enhancements to using UDFs in Apache Spark 4.0?
Yeah, so I think UDFs in general on the batch side, I believe there are some additional enhancements that have happened. But I think we can refer Debabrata to Daniel's talk. I think that should have more details. As far as stateful UDFs, the big feature that is coming for streaming is TransformWithState, of course. That
and just to add to Anish's point, the general UDF optimization on Spark 4.0 is the ability to actually use both columnar format as well as using arrow optimization. So that way, you actually are there's no overhead of serialization between the Py4Jet process and the JVM. You're actually using arrow optimization. So generally speaking, in 4.0 UDFs, we can use in your decorator, you can actually use by arrow, and that would give you the arrow optimization. So yes, there is a huge benefit on that. And we did actually an entire talk on that last month on features in Spark 4.0. So check the link on our YouTube channel on Spark Apache 4.0. Having said that, I think we did a fantastic job. Anish, thank you very much for giving us an expansive view of some of the great features that are available for TransformWithState. It's really a game changer in terms of how extensive the functionality has been, given the arbitrary operators were a bit insufficient and the added functionality that comes with TransformWithState. So thank you very much for that. And those of you who actually joined us from around the globe, thank you for joining us, and hope to see you again in a month when we have another episode of this particular meetup, as well as hoping to see you all on Data Plus AI Summit in June, the first week of June. And thanks a lot for Bo and Eric for answering questions live on LinkedIn and on YouTube. And for the rest of you,